Well, I have this sort of mini matrix epiphany. Well, I don't know about you, but I do. But the idea, again, is that the universe is this great computational engine. It's computing our future or past and so forth. So the idea is that the universe has a sort of state engine and is the laws of physics that give you time evolution from one state in the past to a state in the future, or backwards, as the case may be. And so this is the analogy, which is very, very similar to what a computer does. And so that's sort of my introduction. What I would like to do is now tell you about the research that we've been doing, and that's where the nano kicks in. Again, the point of, Barbara expressed very nicely, the point of making things small is you make lots of them and so forth. And that's really one of the motivations. If we want to go beyond what can be done, say, with silicon, we need to be able to consider materials that have the ability to store and process information at even smaller scales than what is currently possible. And so the materials that we're interested in are these so-called complex oxides. I won't talk too much about them, although I will be talking a lot about them. But not in great depth. But basically, they're complex and they're rich. So they have many properties that are much more than what you would have, for example, in a magnetic material or a semiconductor. They can, in fact, have a great variety of ferroelectric or piezoelectric properties. They can have magnetic properties. They can have the colossal, forget about giant, right? We've got the colossal magnetoresistance. Superconductivity and so forth. All in this, sometimes in a single material. And one of the things that has been very exciting from the research frontier in the last few years is the so-called emergent phenomena at the interfaces between these complex oxides. So the simple equation here is insulator plus insulator equals, so that's the left-hand side, and you can have a metal, a magnetic material, superconductor, and the list goes on, in fact. So the idea is that by making very precise interfaces between ordinary complex oxides, you can get emergent behavior at the interface between those two materials. And this is the system that we're particularly interested in. Lanthanum aluminate, a very thin layer. This is looking in cross-section on a substrate of strontium titanate. They're both complex oxides. They're both insulators by themselves. So it was discovered in 2004 that insulator plus insulator equals metal, or conductor, I should say. And then later on, it was discovered that there's a very sharp transition between the insulating and conducting phase that depends on how many atomic layers you have of this lanthanum aluminate. Magnetic properties have been detected, and superconductivity has been observed in the strontium titanate layer. So this is a very interesting system. Just sort of giving you an idea here. Again, it's a very rich and versatile material, this strontium titanate. And in fact, this is a quote from more than 40 years ago, where Marvin Cohen was describing, in the context of superconductivity in this material, that he wrote that if strontium titanate had magnetic properties, which we now know it does in this interface structure, a complete study of this material would require a thorough knowledge of all of solid-state physics. So one could argue that this material, single material, strontium titanate, is kind of like the hydrogen atom of solid-state physics, that it's such a rich and varied system. And so the question is, well, is it useful for information technology? Is it useful for nanotechnology? So that brings me to the World Cup. I know it's a very segue here, just nanotechnology and the World Cup. We're not talking about buckyballs, but actually I'm talking about, I took a trip, went to a conference around the time of the World Cup in 2006, and I had a ticket to the final that my brother had given me, and in order to justify my existence there, I ended up traveling here and there, giving talks and so forth, before the final, when I was watching the World Cup. So one of the places that I went to was the University of Augsburg, where my friend and host, Jochen Manhart, was showing me this, at the time, unpublished work, where he had seen this very sharp transition between an insulator and a metallic phase of this oxide material. So the idea was that basically, if you have 3 or fewer layers of this lanthanum aluminate, the interface was insulating. If you had 4 or more layers, it was conductor. And right at the interface, right at 3 itself, what they found was that you could switch back and forth between the insulating and conducting phase. So what they did was they applied a large voltage to the back of this strontium titanate substrate. If it was positive, they could switch the interface to a metallic state. And then when they turned off the voltage, it would stay in the metallic state. So it was non-volatile. And then when they made, they reversed the sign, they made it minus 100 volts. It reverted to the insulating state and stayed in that insulating state. So I saw this and I said, oh my gosh, it's a bit. Right? Conducting state is a 1, or maybe you want it to be a 0. We'll let it be a 0. Conducting state is a 0. Insulating state is a 1. It's a bit. Well, what they were doing, though, it was a very big bit. It was kind of like a thumbs up, thumbs down coin type of bit. I mean, it's huge, right? Not really useful. And so, well, I thought, well, maybe there's some way to make it smaller. I was thinking about this. In fact, it ruined my World Cup. It wasn't ruined by that. It was basically ruined by me thinking about how you could make this bit smaller. That wasn't really ruined, but I did miss as did the referees. I missed some critical moments there. But nevertheless, long story, here I am telling you about something that looks a lot like a toy that I used to play with as a child. Now, I did not draw this. I was terrible, actually. I just liked the idea of the Etch-a-Sketch. My brother was much better than I was. But basically, if you were to tear one of these apart, what you would find is that inside is basically a fine aluminum powder. And that powder sticks to the glass or plastic plate that you have here. And when it sticks to it, it becomes a highly reflective, bright surface. And then what you do is you take the stylus and move it around with these knobs, and you scrape off that aluminum powder, and you get a dark region, because now the light goes in and it bounces around, gets absorbed. And so that looks like the dark regions here. But of course, everybody knows the best thing about the Etch-a-Sketch is you turn it upside down, and you shake it, and you restore that bright thing, and you could draw something else, right? That was really the motivation, the inspiration for what we were doing. Of course, we don't work with toys in the lab. We work with tools that cost about 1,000 times more than the Etch-a-Sketch, maybe 10,000 times more. But basically, they work in a very analogous way. So instead of having this big probe that's pointing up, they have a little probe that's pointing down, and it's coated with metal. And that probe makes contact with the surface. You can use this to get the height of the surface. But you can also apply local voltages. And so what we thought of doing was, instead of applying large voltages to the back of this material, we'd apply a smaller voltage to the top and see if we can switch it from the top side. Well, okay, it worked. So here's a picture showing schematically what we do. We apply a positive voltage, and we have, let's say, 2 electrodes on each side, and we can apply a small voltage between the two and monitor the conductance as we are applying this positive voltage and moving the tip from one side to the other. And what we find is that basically what we're doing is we're locally switching the interface from being insulating to being metallic. So again, green is metallic, red is insulating. And when we do this, we see the sudden rise in the current that flows when we have created a wire. So then if we want to know, well, how wide is this wire, for example, what we can do is we can then move across with a negative voltage. And when we do that, we can also monitor the conductance, and we see that there's a very sharp drop. And we can analyze the shape of that drop, and to our surprise, that is a lot sharper than what we expected. In fact, this data corresponds to a wire that was about 2 nanometers wide. So again, for reference, that's about 5 times the distance between equivalent atoms in the material itself. So it's about 4 angstroms between atoms, and this is 2 nanometers, so that's 4 times 5, 20 angstroms. So this is basically also about the size of a diameter of a typical single-wall carbon nanotube. And we can erase them. Okay, so we're still in the process of understanding the details of how this works, but what we believe is that water plays a pivotal central role in this in charging the top surface. So basically, if you have a water molecule, we can pull off or remove this OH minus, leaving a positive H plus here, which attracts an electron to the interface. And that creates locally this conducting region, and then we can change the sign of the tip voltage and remove that H plus, and then maybe another water molecule will come back and complete the cycle. So we call it a water cycle, and we've done some experiments which seem to support this idea. But again, this is very similar to what I was showing you before about a transistor, because you have, well, in this case, we have a gap between 2 wires, let's say, shown in cross-section. If we fill in the gap here, then we can have electrons flowing at the interface between the 2 sides. And we can remove it, for example, and that's basically like a transistor. So this is a 2-dimensional thing that we can control. So it's like a transistor material. Okay, so it's very much similar to what we have in silicon or other types of transistors.